right, guys, Buckley here. I want to go through and show you guys in more detail actually how to solve a system of equations. System of equations comes up quite a bit in statics when we're dealing with 3D particle equilibrium problems, and then when we get into 3D rigid body problems, you may encounter the same thing. So I'm going to do a couple things here. First, I want to remind ourselves, I'm going to use this problem that I did in class as the example for how to solve a system of equations in a little bit more detail. I'm going to pick up from class, so I'm not going to start with the full sum of the forces at A and getting the forces along a line and all of that. Refer to your class notes on that, please. So I'm going to pick up at the point where we know what the vector expression is, and I'm going to show you how this system of equations we can convert that into sort of a matrix form. And then we'll go through and I want to show you how to solve in matrix form the system of equations I'll do the TI-85 calculator, and then I'll also show you just what the code would look like in Matlab to get the same answer. Okay, so here's what we're going to do. So let me walk you through where we are here. We have a sum of the forces is equal to 0 at point A, right, which has 1, 2, 3, 4 cables coming off of it. Sum of the forces equal to 0 is tension in AB, so TAB plus TAE plus TAD plus TAC, and we know the magnitude of AB, which is given as 40, okay? So we've got an expression here that has three unknowns in it: the magnitude TAB, AE, the magnitude TAD, and the magnitude TAC. Okay, and we're going to wind up adding all of these together. So I'm going to just be a little more explicit than I was in class how this works when we add it together. Okay, so these guys together are all going to sum up to 0. So 0, 0, 0 is equal to, in the x direction, I'm going to have 40 minus TAE. Actually, let me do it this way. Because this is going to get cumbersome, I'll write x, y, and z out, okay, rather than having it this way. So in x, I've got 0 is equal to 40 minus 0.447 TAE minus 0.811 TAD minus 0.845 TAC. In y, I have 0 is equal to 0 minus 0.894 TAE plus 0.324 TAD plus 0.169 TAC. And in z, my expression gives me 0. 0, the 0 is equal to 0. TAE has 0 here, plus 0, plus, now I'm on this component, 0.487 TAD minus 0.507 TAC. Okay, so this is my system of equations that I'm trying to solve, and you can see it's pretty nasty, right? So I've got my x expression has all three unknowns in it. My y expression has all three unknowns in it. My z expression has 2 out of the 3. So the way that I would solve this long form, if I wanted to, is basically start with z and express TAD as a function of TAC. Then I would plug that up here, right? And I would solve TAE as a function of TAC. And then I'd plug that and this back up here and then solve the last one, right? So that winds up being quite nasty. So an easier way to tackle this would be to recognize that this is actually the long form of a system of equations written in matrix format. So the way that I would do this is I would say, okay, I'm going to create a vector that is TAE, TAD, TAC, right? And I'm going to multiply that times some quantity, right? Some 3 by 3 matrix. So I've got a 3 by 3 matrix I'll leave that blank for just a sec, times this vector, T A E, T A D, T A C, my three unknowns, is equal to this resultant on the other side. So the way that I would get this resultant is I would move everything over to the other side, right? Anything that doesn't contain a multiplier that's one of these terms, right? So this would move over, so that would be negative 40, and then this is 0, and this is 0, 0, 0. Okay, and in here I would have all of the multipliers. So I would have negative 0.447, negative 0.811, negative 0.845, negative 0.894, positive 0.324, positive 0.169, 0, 0.487, negative 0.507. Okay, so let me double check that this works. So the way the matrix works is I would take this row times this column should equal this number, right? So I would have, I'm just going to do one row to prove that it works. So I'm going to just do we'll call this a gut check, okay? Is this working? Gut check. So I'm going to take this guy times this guy, and it should equal this number. So this would be negative 0.447 TAE minus 0.811 TAD minus 0.845 TAC is equal to negative 40. Let me check this versus my x expression. So if I move this guy over, that's negative 40 on this side, and I got minus 0.447 TAE, minus 0.811 TAD, minus 0.845 TAC. So this checks out, okay? So the way that I've arranged this, right, in this matrix format works. All right, in class, I called this quantity here, this 3 by 3 matrix, I called it K and denoted it with a line underneath. I denoted this guy as T, which makes sense because it's my unknown tensions, and I denoted this guy as R. This is a matrix, right, 3 by 3. This is a vector, 3 by 1, and this is a vector, 3 by 1. I could call this whatever I want to call it, okay? So I'll start off calling it this. So what I have is the expression KT matrix, 3 by 3 matrix times 3 by 1 vector is equal to R, which is my 3 by 1 vector. Now I'm going to multiply both sides by the inverse of K, K inverse, right? K inverse times K is actually equal to I. I is a special matrix that looks like this, 1, 1, 1, 0, 0. Okay, it's the identity matrix. It's the same as sort of like 1, okay? So this winds up going away, and what I get is T, oops, that should be a wavy, T, the vector, is equal to K inverse R. Okay, so just because, now what we're going to do is we're going to go into, first we'll do the TI calculators. I'm going to be using a TI 84, I think, emulator. But it should be the same. The buttons are just basically in the same place on whatever version TI calculator you have. And then I'll show you the code for Matlab. But please note that for the examples in the TI calculator, I've renamed these, okay? So because there's no pre-programmed matrix called K, I'm actually calling this A. So K, or A, is equal to K, okay? It's just a new name, right, for it. And because it's convenient, I've also called B is equal to R. Okay, so don't be confused. I'm just using slightly different naming convention here than I used in class. Okay, so now over to the TI-84. I'm just going to show you. It's just going to be a little video here of me clicking buttons on how to enter in our K matrix, which is going to be named A, and our R vector, which is going to be named B, and how to take the inverse to get quantities here. So the answer that we've been getting for T, let me just show you that. I've been getting T is equal to this vector quantity, which is 11.66, 21.44, and 20.59. And those values are in pounds. Note that this guy, so this breaks down once I look at here, TAE is going to be 11.66 pounds. TAD is equal to 21.44 pounds, and TAC is the last here, which is 20.59 pounds. Okay? All right, let's go look at the emulator. Okay guys, now that you've seen how to use your TI calculator to solve a system of equations, we're also going to show you how to do it in Matlab. So Matlab is even easier, it's just a little bit of code. So I have a little Matlab simulator here that I've got a screenshot of. So basically I'm using the same variable names, so A instead of K, right, from the example, B instead of R. The only thing to note are to make sure that you've got your entries in the correct way, right? So making sure that rows, so your entries for K, negative 0.447, space, negative 0.81, space, negative 0.845. Then to start a new line, you want the semicolon, negative 0.894, blah, blah, blah. When you hit enter there, you should be able to see your matrix in the right format. So that 3x3 matrix for A looks correct. B, you want it to be a vector, so that should be a 3x1 arrangement, not a 1x3. So after every entry, you want to make sure that you have a semicolon, negative 40, semicolon 0, semicolon 0. And then the function that you want is inverse, so in inv, parentheses A, star B, and you'll notice that gives you the same exact numbers that we've been dealing with, right? So there you go. So even simpler in Matlab if you can just fire up a window. All right, so just to refresh for everybody, what we've done is we were a little bit more explicit about how we went from a system of equations written sort of in vector form, x, y, and z, to the matrix form of that. Then how we use matrix operations to actually solve that. We did a demo on the TI calculator as well as here in Matlab. All right, guys, thanks. Enjoy.